Saturn has a magnetic field that should not exist. Every physical law we have says a perfect magnetic field destroys itself. Saturn's field is almost perfectly aligned. It has been for over 40 years of measurements, and every new measurement makes it look more impossible. We'll go inside a planet where it rains liquid helium, where hydrogen turns into metal, and where the rings themselves are wired to the core like a circuit. If you enjoy this journey, subscribe and hit the bell. New chapters drop every week. This is one of the strangest confirmed mysteries in our solar system. Let's begin. In 1934, a British physicist named Thomas Cowling sat down with a pencil and a stack of equations and proved something that would stand as law for the next 90 years. He proved that a perfectly symmetric magnetic field cannot power itself. A magnetic field needs a dynamo to stay alive. A dynamo is basically a churning engine of hot, electrically conducting fluids spinning deep inside a planet, and Cowling's math showed something specific. That engine has to be uneven. It has to wobble. It has to tilt. If the field is too clean and perfectly aligned, the engine stalls, the currents die, the field fades out. Cowling called this the anti-dynamo theorem, and for 9 decades, every planet we checked confirmed it. Earth's magnetic field tilts 11 degrees off its rotation axis. Jupiter tilts almost 10. Uranus tilts 59 degrees. These tilts are the wobble the dynamo needs. They are proof the engine is running. Then we looked at Saturn. Saturn's magnetic field tilts less than 7/1000ths of a degree. To picture that, take a football field and tilt one end up by less than 1/4 of an inch. That is the tilt in Saturn's magnetic axis. It is so close to zero that it essentially breaks Cowling's rule. The field should be impossible. The engine should have stalled long ago. But Saturn's magnetic field is alive. It has been alive for billions of years, and we have no fully agreed upon explanation for how. When Pioneer 11 flew past Saturn in 1979 and measured that tiny tilt, scientists assumed there was an error. The instruments were imprecise. The flyby was too fast. Surely the real tilt was larger. So they waited for better data. Voyager 1 came in 1980. It gave a tighter measurement. The tilt shrank. Voyager 2 came in 1981. It shrank again. Cassini arrived in 2004 and spent 13 years orbiting Saturn, carrying the most precise magnetometer ever sent to an outer planet. By the end of its mission, after 22 close-in dives through the gap between Saturn and its innermost ring, Cassini placed the tilt at less than 7/1000ths of a degree. Confirmed, no instrument error, no misreading. Saturn's magnetic field is real, and it is so perfectly aligned that standard planetary science has no clean answer for why it exists at all. What makes this stranger is that Saturn's field is powerful. Its magnetic moment, which measures the overall strength of a magnetic field, is roughly 600 times greater than Earth's. If you could see magnetic fields with your eyes, Saturn's would be enormous. It would dwarf everything around it. Yet at the planet's surface, the field measures only about 1/3 the strength of Earth's surface field. The reason is pure geometry. Saturn is so much bigger that the field spreads out over a vastly larger volume, diluting its surface intensity even while the total power stays enormous. So we have a planet with a massive, ancient, and very much alive magnetic field. A field so clean and perfectly aligned that every equation we have says it should have burned out. And for over 40 years, the best scientists on Earth have been trying to figure out why it hasn't. They still don't have a final answer, and the deeper they look, the stranger it gets. September 1st, 1979. A spacecraft the size of a trash can lid was screaming through space at 71,000 miles per hour. Pioneer 11 had been traveling for 6 years. It launched in April 1973 from Cape Canaveral with one goal: get close enough to Saturn to take readings. No spacecraft had ever done it. Nobody knew what was out there. As it closed in, Pioneer 11 skimmed within 13,000 miles of Saturn's cloud tops. For reference, that gap is roughly the width of the continental United States. For a planet 300,000 miles wide, it was razor close. On board was a magnetometer, a device that detects and measures magnetic fields. Scientists knew the big planets in our solar system generated magnetic fields. Jupiter had one, Earth had one, Saturn almost certainly had one too. They expected to measure it, record the tilt, and move on. The tilt they measured was less than 1 degree. That number stopped people cold. Every other planet they had measured had a noticeable tilt. Earth's field wobbles 11 degrees. Jupiter's tilts nearly 10. Those tilts are the fingerprints of a working dynamo engine. A tilt close to 0 was supposed to be physically impossible for a sustained magnetic field. And yet here was Saturn, showing 1. The scientific reflex at the time was doubt. Instruments fail. Flybys are fast. The Pioneer magnetometer had not been calibrated to catch something this strange. Scientists assumed the real tilt was probably larger and that something in the measurement had smoothed it out. They logged the result, flagged the anomaly, and waited. They did not have to wait long. Voyager 1 arrived in November 1980. It carried better instruments. It measured a tilt of less than 7/10 of a degree, smaller than Pioneer's estimate. The scientists ran the numbers again. Same result. Voyager 2 came in August 1981. Its measurements matched. The tilt was real, and it was tiny. At that point, the anomaly hardened into a genuine mystery. 3 independent spacecraft with 3 independent instruments had all arrived at roughly the same conclusion. Saturn's magnetic field was almost perfectly aligned with its rotation axis. To be clear about what that means physically, a planet rotates around an axis like a top spinning on a table. Its magnetic field also rotates around an axis. On most planets, those 2 axes point in slightly different directions. The gap between them is the tilt. On Saturn, those 2 axes point in almost exactly the same direction. They are nearly identical. Cowling's math said that should kill the dynamo. The fluid motions generating the field require asymmetry to sustain themselves. A perfectly symmetric setup means no net current loops, and without current loops, no field. But Saturn's field was there, confirmed across 3 separate missions. Ancient, strong. The leading researchers at the time had no good answer. Some suggested a hidden asymmetry too small to detect. Some proposed the dynamo operated differently in metallic hydrogen than in liquid iron, the way Earth's dynamo does. Some quietly wondered if the math itself was missing something. None of them knew that the mystery was about to get significantly worse. The next mission to Saturn would not arrive for more than 2 decades, and when it did, the tilt would be even smaller than anyone had measured. Deep inside a planet, something is moving. It is not rock. It is conducting fluid, super hot, and under pressure so extreme that the material behaves in ways nothing on the surface can match. And it is spinning, churning, looping, driven by 2 forces, the planet's own rotation and the heat bleeding outward from the core. This is the planetary dynamo, and it is the reason Earth has a magnetic field, Jupiter has a magnetic field, and Saturn has a magnetic field. Here is the basic picture. A planet's interior is layered. The deeper you go, the hotter and denser things get. On Earth, below the rocky mantle, there is a layer of liquid iron and nickel. That layer is conducting, meaning electricity can flow through it. As the planet rotates, the fluid rotates too. And because it is also convecting, meaning hot material rises while cooler material sinks, the fluid moves in complex spiraling patterns. Those spiraling patterns carry electrical charge. Moving electrical charge generates a magnetic field. That magnetic field, in turn, pushes back on the fluid, shaping how it moves. The fluid shapes the field shapes the fluid. They sustain each other in a loop that can run for billions of years. That feedback loop is the dynamo. Now here is the critical detail. For the loop to stay alive, the fluid motions have to be asymmetric. They have to create current patterns that are uneven, slightly chaotic, and most importantly, tilted relative to the planet's rotation axis. That tilt is what keeps the dynamo self-reinforcing. Thomas Cowling's 1934 theorem proved the math behind this. A perfectly symmetric dynamo, one where everything flows in perfect circles, aligned exactly with the rotation axis, generates currents that cancel each other out. The magnetic field collapses. No tilt means no sustained field. Every planet we know confirms this. Earth's tilt, 11 degrees. Jupiter's, almost 10. Even Mercury, with its relatively weak field, tilts 14 degrees. Saturn's dynamo is generating a field in conditions that should prevent one from forming. And the reason why gets into something unusual. Its dynamo does not run on liquid iron. Saturn's core sits surrounded by an ocean of something that does not exist naturally anywhere on Earth. Metallic hydrogen. Under pressures millions of times greater than atmospheric, hydrogen stops being a gas or a liquid in any normal sense. Its electrons break free, and the material begins conducting electricity like a metal. It becomes what scientists call metallic hydrogen, and it is inside this metallic ocean that Saturn's dynamo runs. The fluid dynamics in metallic hydrogen are different from those in liquid iron. The viscosity is different. The way heat moves through it is different, and critically, the way the field interacts with the fluid is different in ways scientists are still working out. What makes Saturn so baffling is that its metallic hydrogen dynamo is generating a powerful, ancient, sustained magnetic field in a configuration that should, by every rule we have, be impossible. The field is alive. The dynamo is running. And the reason it can maintain near-perfect symmetry while still sustaining itself is what makes Saturn one of the strangest objects in the solar system. The answer is buried in layers we cannot see directly, and each layer has its own secret. Imagine lining up every planet with a magnetic field and checking their tilts one by one. What you find is a pattern so consistent it looks like a physical constant of nature. Earth, 11 degrees. Jupiter, 9.6 degrees. Uranus, 59 degrees. Neptune, 47 degrees. Mercury, 14 degrees. Every single one of them tilts. Every single one of them keeps their dynamo alive by doing exactly what Cowling's math says they must. The field tips away from the rotation axis. The fluid motions stay asymmetric. The engine runs. Now add Saturn to the list. Less than 7/1000ths of a degree. One of these planets is doing something fundamentally different. Earth's tilt of 11 degrees means that if you followed a compass needle to its true end, you would arrive somewhere in the ocean north of Canada, not at the geographic North Pole. The gap is measurable, consistent, and caused directly by the slight offset between Earth's spinning rotation axis and the axis of its internal magnetic field. This offset is the sign of a working tilted dynamo underneath. Jupiter's tilt is even more dramatic. At 9.6 degrees, Jupiter's magnetic field produces complex, asymmetric patterns visible in the behavior of its charged particle belts and in the radio emissions it broadcasts into space. Scientists use that tilt as a way to track Jupiter's internal rotation, the way you might use a clock hand to tell time. Uranus is in a category of its own. Its field tilts 59 degrees from the rotation axis and is offset significantly from the planet's center. The result is a magnetic field so lopsided and irregular that it changes dramatically depending on where you are around the planet. Uranus is essentially tumbling magnetically. Neptune's 47-degree tilt creates a similarly chaotic field. Both of these ice giants may have their extreme tilts because of unusual interior structures, possibly involving liquid water or ammonia acting as the conducting layer instead of metallic hydrogen or iron. Their dynamos are messy, but they obey the rule: the tilt is there. Even Mercury, the small, slow-spinning innermost planet, has a magnetic field tilted 14 degrees. Mercury's field is weak, roughly 100 times weaker than Earth's, and scientists long debated whether its slowly cooling iron core could sustain a dynamo at all. The answer turned out to be yes, and the field shows the expected tilt. The pattern is clear. Across rocky planets and gas giants, across planets with iron cores and planets with metallic hydrogen interiors, across planets close to the star and planets in the outer dark, every sustained planetary magnetic field carries a measurable tilt away from the rotation axis. The rule holds. Saturn is the only exception confirmed by measurement. Scientists have proposed various reasons why Saturn might be special. Maybe its interior is structured in a way no other planet matches. Maybe the material inside it, metallic hydrogen mixed with helium rain, creates conditions that allow a near-symmetric dynamo to survive. Or maybe Saturn is doing something so unusual that it requires a category of explanation that does not yet fully exist in planetary science. What is certain is this: Saturn is alone. Every other planet falls in line. Saturn refuses to, and understanding why means going deeper inside Saturn than any instrument has ever reached. It means understanding what the inside of this planet actually looks like. And that picture, once you see it, is genuinely unlike anything else in the solar system. Scientists have a standard response to a strange number. They measure again. If the second measurement agrees with the first, they start to take it seriously. If it keeps agreeing across multiple independent instruments across decades, the strange number stops being a possible error and starts being a fact that demands explanation. Saturn's near-zero magnetic tilt has now been measured 4 times by 4 separate spacecraft across 45 years. Each measurement has pushed the number smaller. Each measurement has made the mystery harder, not easier. Pioneer 11's 1979 flyby gave the first number, less than 1 degree. The instruments were early generation. The pass was fast. Scientists flagged the result as interesting, but held it loosely. Voyager 1 arrived in 1980 with updated magnetometer hardware. It refined the tilt to less than 0.7 of a degree. The number had dropped. Scientists took note. Voyager 2 followed in 1981. Its reading agreed with Voyager 1. 2 spacecraft with independent instruments pointing to the same result was harder to dismiss. The tilt of Saturn's magnetic axis, whatever it was, appeared genuinely small. Something was different about Saturn. Then came the longest gap in the story, from 1981 to 2004. No spacecraft visited Saturn. Scientists worked with the Voyager data and debated whether the tilt might be hiding some asymmetry too subtle to detect, or whether Saturn's interior was structured in a fundamentally unusual way. Several competing models were proposed. None were tested against new data. When Cassini arrived in July 2004, planetary scientists expected one of 2 outcomes. Either the new measurements would reveal a hidden tilt that Voyager had missed, confirming the standard dynamo model, or they would confirm the small tilt and force a rethinking of the theory. They got the second outcome. Early Cassini data pushed the tilt below 0.06 of a degree, much smaller than Voyager's estimate. But the real confrontation came in 2017. Cassini was running low on fuel. Scientists decided to send it on a final sequence of 22 orbits that would bring it closer to Saturn than any spacecraft had ever flown. These passes went through the narrow gap between Saturn and its innermost ring, a region of space previously considered too dangerous to enter. At those distances, with Saturn's magnetic field far stronger than at Cassini's earlier orbits, the magnetometer data was sharper than anything collected before. The results were published in 2018. The tilt, less than 0.008 of a degree. When the full dataset was analysed, the upper limit fell further to 0.007 of a degree. Confirmed. Every pass agreed. Every instrument agreed. Professor Michelle Dougherty of Imperial College London, who led the Cassini magnetometer team, described the situation with uncommon directness. Each time a more accurate measurement of the tilt is taken, it gets smaller, and at a tilt smaller than 1/100th of a degree, she said it increasingly looks as though scientists will have to rethink the ways different kinds of planets can form magnetic fields. That is a significant statement. It does not say the current model needs adjustment. It says the model may need replacement. 4 missions, 4 decades, a tilt that keeps shrinking towards zero. The mystery did not become easier with better data. It became sharper, cleaner, and more unavoidable. The next question is, what is inside Saturn that could possibly explain this? By April 2017, Cassini had been orbiting Saturn for 13 years. It had mapped the rings. It had photographed the moons. It had watched storms build and collapse in Saturn's atmosphere. And it had spent years collecting magnetic field data from safe wide orbits far above the planet. But the scientists running the mission knew that safe orbits only told part of the story. To get the data they really needed, they had to go closer. The gap between Saturn's cloud tops and the inner edge of the D-ring, the faint, innermost ring, is roughly 1,500 miles wide. That sounds like a lot, but for a spacecraft moving at tens of thousands of miles per hour, threading that gap was a genuine engineering challenge. The risk was a particle strike at high velocity, which could disable or destroy the spacecraft. Scientists decided to take the risk. They called it the grand finale. Starting April 26, 2017, Cassini began a series of 22 highly inclined orbits, each one sending the spacecraft plunging through that gap between the planet and its rings. Every pass brought Cassini within roughly 1,000 miles of Saturn's cloud tops. At those distances, the magnetic field readings were unlike anything collected before. The field was far stronger, the structure far more detailed, and the signal far cleaner than anything Cassini had recorded from its earlier wider orbits. What the magnetometer found during those dives answered some questions and created entirely new ones. The main answer was the tilt conformation. At close range over 22 separate passes, the tilt of Saturn's magnetic axis was measured to be less than 0.008 of a degree. No hidden asymmetry emerged. The field was not hiding a larger tilt that previous measurements had missed. The near-perfect alignment was real at every depth and angle measured. But hidden inside that near-perfect field was something unexpected. When scientists analyzed the data in detail, they found faint magnetic variations layered within the main field, stripe-like patterns banded by latitude, barely detectable against the overwhelming symmetry of the main dipole. These stripes matched the widths of Saturn's visible wind bands in the atmosphere. Something was generating a secondary magnetic signal. Something shallow, close to the surface, was adding its own faint imprint onto the main field from below. The grand finale also detected an electric current running between Saturn's innermost D-ring and the planet's upper atmosphere. The rings, which most people think of as passive debris, were electrically connected to the planet. There was a live current flowing between them. On September 15, 2017, after the 22nd dive, Cassini fired its thrusters one final time and deliberately plunged into Saturn's atmosphere. It burned up in seconds. The mission ended. The data it left behind has kept planetary scientists busy ever since. The grand finale produced more detailed magnetic field measurements than all previous Saturn missions combined. And the picture it gave of Saturn's interior was strange enough that multiple teams around the world immediately began proposing new theories to explain it. 2 things were now clear. Saturn's near-perfect magnetic alignment was confirmed beyond doubt, and something inside the planet was generating a second magnetic field on top of the first. Understanding that second signal meant going deeper into Saturn's interior than any instrument had ever seen. Numbers in planetary science can be hard to feel. They are often too large or too small for the human brain to naturally grip. So here is a way to picture 7/1000ths of a degree. Take a standard American football field. It is 100 yards long, which is 300 feet. Now tilt one end of that field upward by less than 1/4 of an inch. That tiny, barely perceptible rise is the angle of Saturn's magnetic tilt. You could not feel it standing on the field. You could barely see it with careful measurement. It is, for all practical purposes, zero. Now consider that Cowling's anti-dynamo theorem says that a magnetic field maintained at exactly zero tilt should be self-destroying. The engine that powers the field requires asymmetry. It requires the slight wobble. Take the wobble away, and the currents that sustain the field cancel each other out. The field dies. Saturn's tilt is not exactly zero, but it is so close that the gap between exact zero and Saturn's actual tilt is smaller than scientists can currently measure with any instrument. The field is alive, the engine is running, and the tilt is so small it falls below the detection limit of the most precise magnetometer ever sent to another planet. To appreciate how extreme this is, compare it to Earth. Earth's magnetic axis tilts 11 degrees from its rotation axis. That is enough of a wobble that a compass in Alaska points toward northern Canada, not toward the geographic pole. The tilt is measurable with equipment you could buy at a sporting goods store. Saturn's tilt is roughly 1,500 times smaller than Earth's. If you scaled Earth's tilt down proportionally, you would end up with a compass that deviates from true north by the width of a human hair at arm's length. Jupiter's tilt, nearly 10 degrees, is easy to detect from Earth using radio telescopes. Uranus tilts 59 degrees, which means its magnetic equator is nowhere near its geographic equator. These are obvious, dramatic tilts that fall comfortably within what standard dynamo theory predicts. Saturn does something none of them do. Saturn generates a massive, sustained, ancient magnetic field with a tilt so small that every accepted model of planetary dynamo physics has struggled for 45 years to explain it. And here is the part that deepens the problem. Saturn's field is powerful. It has a magnetic moment roughly 600 times greater than Earth's. The engine is not weak or fading, it is vigorous and ancient, and enormously strong. Whatever is sustaining it is doing so with a kind of precision that does not appear anywhere else in the solar system. Some researchers have framed this as Saturn approaching the theoretical limit described by Cowling's theorem. The theorem says zero tilt is impossible. Saturn appears to be testing that limit from as close as possible without actually crossing it. If it is crossing it, we do not yet know how. What is known is that the answer must come from something inside the planet, something deep, something that filters, shapes, or suppresses the tilt before the field reaches the surface. And understanding that requires understanding what Saturn is actually made of on the inside. That interior turns out to be one of the most extreme environments in the solar system. If you could cut Saturn in half and look at a cross-section, you would see something that looks nothing like Earth's clean textbook layers. Saturn is not a solid planet with a liquid core beneath a solid shell. It is a planet where the materials change state gradually under pressure, where the line between gas and liquid blurs and then disappears, and where familiar elements like hydrogen and helium behave in ways that have no counterpart on Earth. Start at the top. In the cloud bands you can see through a telescope. That region is molecular hydrogen and helium, the same forms those elements take in everyday chemistry. The clouds themselves are made of ammonia ice crystals and ammonium hydrosulfide. The temperature here is around -220 degrees Fahrenheit, brutally cold, and the wind speeds reach over 1,000 miles per hour in some bands. Now go deeper. As you descend, the pressure increases. By roughly 600 miles down, the pressure is so high that the gas no longer behaves as a gas. It becomes a dense, superhot liquid. The temperature at this depth is already thousands of degrees Fahrenheit. The boundary between atmosphere and liquid is gradual. There is no clear surface, no ocean with a shoreline. The planet just gets denser and hotter. Go deeper still. Around 12,000 miles below the visible cloud tops, something dramatic happens. The pressure crosses 1 million times atmospheric pressure. At that point, liquid hydrogen transitions into metallic hydrogen. Its electrons are stripped free. The material begins conducting electricity. It starts to behave like a metal, even though there is no solid structure at all. This is the dynamo region. This is where Saturn's magnetic field is born. But even below the metallic hydrogen layer, the story continues. Near the boundary between the metallic hydrogen and the core, conditions become even more extreme. Temperatures approach 21,000 degrees Fahrenheit. The core itself, a mixture of rock, iron, and other heavy elements, has a diameter estimated at around 16,000 miles. For comparison, Earth's total diameter is about 8,000 miles. Saturn's core is twice as wide as our entire planet, and that core may be far stranger than a simple ball of rock and iron. Recent analysis of how Saturn's rings vibrate in response to interior motions, a technique called ring seismology, suggests the core may be diffuse and spread out, potentially filling up to 60% of the planet's total radius. A fuzzy, extended core rather than a compact ball. This would change every model of how Saturn's dynamo operates. The interior also radiates enormous heat. Saturn puts out roughly 2.5 times more energy than it receives from its star. Some of that energy comes from the core, but a significant portion comes from a process happening within the layers above the core, a process that turns out to be central to the magnetic mystery. Each layer of Saturn's interior influences the layer above it. Each one shapes the magnetic field differently. And somewhere between the deep metallic hydrogen and the surface clouds, something is doing something unusual to the field. Something is making it almost perfectly clean. Hydrogen is the simplest element in the universe. One proton, one electron. Under normal conditions, it is a colorless gas, lighter than air, highly flammable, and completely non-conductive. Now squeeze it. Squeeze it harder than you have ever imagined squeezing anything. Squeeze it under pressures 1 million times greater than the pressure at sea level on Earth. Squeeze it so hard that the electron, which normally orbits its proton at a fixed distance, gets forced into a shared electron sea with all the surrounding hydrogen atoms. At that point, hydrogen stops being hydrogen as we know it. It becomes metallic hydrogen. Metallic hydrogen looks and behaves nothing like the gas at the top of Saturn's atmosphere. It is a liquid metal, conducting electricity the way copper or silver does, but without any solid crystal structure. It is a quantum material, one where the familiar rules of chemistry no longer apply. On Earth, metallic hydrogen can only be created in laboratories under extreme conditions, and only for fractions of a second. Inside Saturn, it exists in a layer thousands of miles thick, and it has existed there for billions of years. This is where Saturn's magnetic dynamo runs. The metallic hydrogen layer sits roughly 12,000 miles below Saturn's cloud tops and extends downward toward the core. Within this layer, the electrically conducting fluid convects. Hot material rises, cooler material sinks. Saturn's 10.5-hour rotation twists these rising and sinking flows into spiraling columns. Those spiraling columns carry electrical current. That current builds the magnetic field. This is the same basic process as Earth's liquid iron outer core. Different material, same fundamental physics. The conducting fluid moves. The movement generates current. The current generates the field. But here is where Saturn diverges from Earth in a critical way. In Earth's core, the fluid is liquid iron. Iron, under those conditions, is a relatively simple conductor. It convects in ways that planetary scientists have studied and modeled extensively. Earth's magnetic field, with its measurable 11-degree tilt and its gradual pole reversals every few 100,000 years, is reasonably well explained by those models. Saturn's metallic hydrogen is different. The way it responds to pressure changes, temperature gradients, and the planet's rotation creates a dynamo that is far harder to model. And critically, it does not exist in isolation. Above the metallic hydrogen layer, In the transition zone between the metallic and molecular hydrogen, something else is happening that may be the key to the entire mystery. At that transition zone, pressure and temperature reach a specific combination where helium, which is mixed with hydrogen throughout Saturn's interior, starts to do something strange. It stops mixing, it forms droplets, and those droplets begin to fall. This is the process that may explain why Saturn's magnetic field appears so clean. But understanding how falling droplets of helium could shape an entire planetary magnetic field requires understanding something that sounds physically impossible. A planet-wide rainstorm inside a gas giant, falling through a material that has no surface, no clouds, and no sky. On Earth, rain forms because water vapor rises, cools, condenses into droplets, and falls back down through the atmosphere. It is a cycle driven by temperature and gravity. The droplets fall through air. Inside Saturn, something similar happens, but the scale is planetary. The material is helium, and the droplets fall through liquid metallic hydrogen. Here is how it works. Throughout Saturn's outer layers, hydrogen and helium are mixed together, the way two liquids might be blended in a solution. But as you go deeper, pressure and temperature increase, and at a specific depth within the metallic hydrogen zone, that mixture becomes unstable. Helium becomes immiscible, which means it can no longer stay dissolved in the metallic hydrogen around it. Think of it like oil and water. If you shake oil and water together, they temporarily mix, but let them sit and the oil separates and floats to the top. Inside Saturn, helium does the same thing, except in reverse. Helium is denser than the surrounding metallic hydrogen at those depths, so instead of floating up, it separates into droplets and falls. Those helium droplets rain downward through the metallic hydrogen, sinking slowly toward the core. As they fall, they release gravitational energy as heat, and that heat contributes to something measurable from the outside. Saturn radiates 2.5 times more energy into space than it receives from its star. For a planet that formed billions of years ago, simply cooling off should not produce that much excess energy. The helium rain is an internal heat source, a slow planetary engine fueled by gravity alone. This was first proposed in the 1970s and has since been supported by spacecraft measurements and computer modeling. It is now widely accepted as a real process occurring inside Saturn. The helium rain is confirmed as a working theory supported by strong evidence, though its precise depth, thickness, and rate remain areas of active study. But the helium rain turns out to be far more than just a heat source. It creates a structural feature inside Saturn that may explain the magnetic mystery. As the helium rains out, it creates a zone within the planet where the fluid is stably stratified. This means that the material in that zone cannot freely convect. Warmer fluid cannot rise through it. Cooler fluid cannot sink through it. The normal convective churning that drives a dynamo is suppressed. The stably stratified zone acts like a barrier, a layer of calm water between two stormy regions. Below it, in the deep metallic hydrogen where the pressure is high enough that helium mixes freely again, vigorous convection continues. The deep dynamo runs normally down there, generating a full magnetic field with all its complex structure, including components that are tilted and asymmetric. But above the stably stratified zone, where the dynamo signal rises toward the surface, something happens to those tilted components. They get filtered out. The implications of that filtering process are what planetary scientists have been untangling ever since Cassini gave them the data to do it. Imagine a radio transmitter buried underground. It is broadcasting on dozens of frequencies at once. Some of those frequencies travel easily through the rock and soil above. Others get absorbed, blocked, or dampened before they reach the surface. By the time you pick up the signal above ground, only certain frequencies remain. Saturn's interior works like that. And the helium rain layer is the filter. Here is the mechanism. Deep inside Saturn, below the helium rainout zone, the metallic hydrogen convects freely. That convection generates a full dynamo field. and that field has structure. It has a primary component, the main dipole, which is the large-scale north-to-south field that dominates everything. But it also has secondary components, tilted parts, asymmetric swirls, non-symmetric contributions that in other planets would show up as the measurable tilt between the magnetic and rotation axes. Those secondary components are what Cowling's theorem requires. Without them, the dynamo should not sustain itself. In most planets, those secondary components rise through the interior and reach the surface. Scientists measure them as the tilt, Earth's 11 degrees, Jupiter's 10. The wobble is visible because nothing between the deep dynamo and the surface removes it. In Saturn, the helium rainout zone intercepts those components before they reach the surface. The physics of Y comes down to what the stably stratified zone does to magnetic field components of different shapes. The primary dipole, the main symmetric field, is large-scale and robust. It passes through the stratified layer relatively unchanged. The non-axisymmetric components, the tilted and asymmetric parts of the field, are smaller scale and structured differently. When they encounter the stably stratified layer, that layer damps them. The fluid in the stratified zone cannot convect freely, so it cannot support the kind of complex motions that would carry those smaller scale field components upward. They get suppressed below the filter. They never reach the surface. What the surface sees is only the primary dipole, clean, symmetric, and nearly perfectly aligned. The tilt appears to vanish. This theory was developed in detail by a team at Johns Hopkins University. Their computer simulations, published in 2021, showed that a helium rainout layer extending from roughly 40% to 70% of Saturn's radius could produce exactly the kind of magnetic field Cassini measured. The thicker the filter layer, the cleaner the surface field. Their best models required the helium rainout zone to be extremely thick, and they found that slightly stronger cooling at Saturn's poles compared to its equator helped match the specific details of what Cassini observed. A 2025 follow-up study fed the actual Cassini grand finale measurements directly into the model and found specific requirements for Saturn's internal temperature distribution. The match was good. The helium rain filter remains the leading explanation for Saturn's near-perfect symmetry, but it is still a theory. No spacecraft has ever directly sampled Saturn's interior at those depths. The helium rain zone has never been observed directly. Scientists infer its presence from the field it presumably produces and from the excess heat Saturn radiates. And the theory does not explain everything. There are other features of Saturn's magnetic field that the filter alone cannot account for, features that suggest something additional is happening much closer to the surface. Cassini's grand finale measurements did not just confirm the near-zero tilt, they gave scientists enough data to map the internal structure of Saturn's magnetic field in unprecedented detail. When researchers analyzed the full dataset from those 22 close-in dives, they found something they had predicted, but had never directly confirmed. A region deep inside Saturn, where the magnetic field changes character. A boundary layer where the complex, structured field from the deep dynamo transitions into the clean, symmetric field seen at the surface. This boundary corresponds to a stably stratified layer at least 2,500 miles thick. To put that in perspective, 2,500 miles is roughly the distance from Los Angeles to Chicago, and then from Chicago to New York, combined. It is a zone that spans a significant fraction of Saturn's total radius. This layer sits above the deep metallic hydrogen dynamo and below the molecular hydrogen envelope. In this zone, the fluid does not convect freely. The helium rainout creates a density gradient that suppresses the usual rising and sinking of hot and cool material. The fluid is stable in the way that a calm lake is stable. Layers do not mix unless something very powerful forces them to. For a magnetic dynamo, that stability is both a filter and a puzzle. The filter aspect is what the previous chapter described. Non-symmetric field components get dampened as they try to rise through the layer. The puzzle is different. If the layer suppresses convection so effectively, how does any magnetic information escape at all? How does the primary dipole push through if the medium it has to cross resists motion? The answer involves the way magnetic field lines behave differently from fluid motions. A large-scale, symmetric dipole field can diffuse through a stably stratified layer even when fluid convection is suppressed, the way a slow electrical current passes through a resistor. Smaller-scale, non-symmetric components are more effectively damped by the same layer, so the filter is selective. It passes the big symmetric field, it blocks the small asymmetric components, and the result at the surface is a field that looks unrealistically clean. Cassini's data gave scientists enough resolution to confirm this 2,500-mile minimum thickness, but it could not determine the maximum thickness or the exact density structure within the layer. Those details depend on the helium rainout rate, the temperature gradient, and Saturn's internal heat flow, none of which are directly measurable with current technology. What scientists do know is this: the layer is real, its fingerprint is in the data, its minimum size is established, and its presence is the single strongest piece of evidence that the helium rain filter theory is on the right track. But even with this layer confirmed, the story of Saturn's interior is far from complete, because sitting above this filter, in the zone between the stably stratified layer and the outer atmosphere, something else is generating its own magnetic signal. And that signal has a shape that matches something you can see with a backyard telescope on a clear night. Hold a rock in sunlight, it warms up. When you take it into the shade, it gradually cools. The rock puts out the same energy it absorbed from the light. Eventually, it reaches equilibrium, and it stops glowing with any extra warmth. Planets do the same thing, broadly speaking. They absorb energy from their star, warm up, and radiate that energy back into space. A planet that has been in place for billions of years should have reached a rough equilibrium between energy in and energy out. Saturn violates this. Saturn radiates approximately 2.5 times more energy into space than it receives from its star. Every second of every day, Saturn is pumping out heat that its star did not provide. Where is the extra energy coming from? Part of the answer is simple. Every planet generates some internal heat from radioactive decay in its rocky core and from the gravitational compression that occurred during its formation billions of years ago. Jupiter, for example, still radiates about 1.5 times the energy it receives. That excess is largely leftover formation heat, slowly leaking out. Saturn's 2.5 times excess is significantly higher than what formation heat alone can account for. At Saturn's age and size, models of planetary cooling predict it should be radiating much closer to the energy it receives. Something inside Saturn is providing an additional continuous heat source. That source is the helium rain. As helium droplets separate from the metallic hydrogen and fall deeper into the planet, they release gravitational potential energy. This is the same basic principle as a hydroelectric dam. Material falling through gravity does work and releases energy. In Saturn's case, the falling helium converts gravitational energy into heat throughout the interior. This process has been happening continuously since the planet formed, and the metallic hydrogen layer reached sufficient pressure to make helium immiscible. It is a slow engine running on the planet's own structure, powered by nothing external, sustained by the continuous settling of helium towards the core. The energy released from this process is spread throughout the helium rainout zone and conducted upward through the planet's layers. At the surface, it manifests as excess infrared radiation. Saturn is noticeably brighter in infrared than a passively cooling planet of its size should be. This was first predicted theoretically in the 1970s, before any spacecraft had visited Saturn. When Pioneer 11 and the Voyagers confirmed the excess heat output, the helium rain hypothesis gained strong support. It remains the most widely accepted explanation for Saturn's thermal anomaly. The significance for the magnetic field mystery is direct. The helium rain that produces the excess heat is the same process that creates the stably stratified filter layer. The two phenomena, the glowing planet and the hidden magnetic tilt, have the same root cause. Saturn's extraordinary heat output is essentially the exhaust of the same engine that shapes its magnetic field. A planet glowing too brightly and a magnetic field that should not exist are two symptoms of the same interior process. And that interior has one more surprise waiting in the shallow layers above the filter. Something that Cassini only detected because it flew close enough to catch a faint signal buried beneath the overwhelming main field. Saturn's visible atmosphere is one of the most recognizable sights in astronomy. From a distance, it looks like a series of colored bands running parallel to the equator, pale yellows and tans, separated by subtle boundaries. Those bands are the tops of powerful jet streams, rivers of wind blowing at hundreds of miles per hour in alternating directions, east and west, stacked in latitude like lanes on an enormous circular highway. Scientists have tracked these atmospheric bands for centuries. They are consistent, stable over human timescales, and structured in a way that reflects deep atmospheric dynamics. What nobody expected was to find those same bands reflected in Saturn's magnetic field. During the grand finale dives, as Cassini flew through the narrow gap between Saturn and its rings at altitudes low enough to detect subtle magnetic variations, the magnetometer picked up something unexpected. Layered within the main dipole field, there were faint stripe-like perturbations, tiny variations in field strength organized by latitude. When scientists mapped those perturbations, they matched the widths of Saturn's atmospheric wind bands almost exactly. The atmospheric bands at the surface were casting a shadow into the magnetic field below, or rather, something below the atmosphere was generating a secondary magnetic signal whose structure matched the atmosphere above. To understand why this matters, recall that Saturn's main dipole is generated deep in the metallic hydrogen layer, thousands of miles beneath the visible atmosphere. That deep dynamo produces the dominant field, strong, symmetric, nearly perfectly aligned. But between the metallic hydrogen and the molecular hydrogen above it, there is a transition zone. In that transition zone, hydrogen is partially conducting, not the full metal conductor of the deep dynamo, but still capable of carrying some electrical current. And driving through that partially conducting layer are Saturn's wind systems, the same jet streams that produce the visible atmospheric bands. Those wind systems, penetrating downward from the atmosphere into the semiconducting layer, can generate their own small-scale electrical currents. Those currents produce their own small-scale magnetic field, and that field has the same banded, latitudinally organized structure as the jets that drive it. What Cassini detected during the grand finale was, for the first time, direct evidence of this shallow magnetic signal layered on top of the deep main field. The implication was significant. Saturn does not have a single magnetic dynamo. It has at least two distinct sources of magnetism, operating at different depths. The deep one in the metallic hydrogen produces the dominant field. A shallower one in the semiconducting layer produces the faint banded signal. This finding answered a question and immediately raised another. One, if there is a shallow magnetic source driven by wind, does it interact with the deep field? Does it influence the tilt? Could it be part of the reason Saturn's main field is so symmetric? And there was a third discovery from the grand finale that made the picture even stranger. The rings themselves appeared to be part of the electromagnetic system. Something was electrically connecting Saturn's innermost ring directly to the planet below. A planet with two magnetic engines, that is what the grand finale data pointed toward. One deep, one shallow, both active, both shaping the field that extends into space around Saturn. The deep engine is the primary dynamo operating in the metallic hydrogen layer roughly 12,000 miles below the cloud tops. That is where the main dipole field originates, where the vast majority of Saturn's magnetic power comes from, and where the near-perfect axisymmetry is generated before being filtered by the helium rain layer above. The shallow engine is something different. It operates in the semiconducting hydrogen layer between the metallic hydrogen below and the insulating molecular hydrogen above. In this zone, hydrogen conducts electricity, but weakly, far less efficiently than the metallic hydrogen beneath it, and the fluid motions driving it are not thermal convection from the interior, but differential rotation. Saturn's powerful atmospheric jet streams extending downward into the semiconducting layer. On Earth, the atmospheric winds do not penetrate deep enough to reach the conducting iron core. The two systems, the atmosphere and the magnetic dynamo, are essentially separate. On Saturn, the jet streams are powerful enough and the transition from insulating to conducting hydrogen shallow enough that the wind systems reach the electrical layer. When fast-moving electrically conducting fluid flows through a pre-existing magnetic field, it generates additional electrical currents. Those currents generate their own magnetic field. This is the shallow dynamo, a wind-driven secondary magnetic source electrically coupled to the deep primary dynamo below it. The shallow dynamo's magnetic signal is weak compared to the deep field. During the grand finale, Cassini could only detect it at the close distances of those final 22 dives. From wider orbits, the deep field overwhelms it completely. But at close range, the banded structure of the shallow dynamo's signal was clear enough to map. The bands in the shallow dynamo's field correspond to the specific latitudes of Saturn's major jet streams. Each band in the field matches a jet stream in the atmosphere. The physics is direct. The faster the wind in a given latitude band, the more electrical current it drives through the semiconducting layer, and the stronger the magnetic signal from that band. This shallow dynamo also helps explain why Saturn's magnetic field has a slight north-south asymmetry in its fine structure, even while the overall field is nearly perfectly symmetric. The jet streams in Saturn's northern and southern hemispheres are not exactly mirror images of each other. The asymmetries in the wind systems create asymmetries in the shallow dynamo signal. What remains unknown is whether the shallow dynamo plays any role in maintaining or suppressing the tilt of the main field. Some researchers have proposed that the interaction between the shallow and deep dynamos could contribute to the near-perfect axisymmetry seen at the surface. Simulations that include differential rotation in a semiconducting layer can reproduce surprisingly small dipole tilts without requiring a thick helium rain filter at all. Both mechanisms may be real. Both may be contributing simultaneously. And there is one more piece of the electromagnetic system that the grand finale revealed, something connecting two parts of Saturn that no one expected to be linked. Picture Saturn's rings as you have always imagined them, billions of chunks of ice and rock, ranging from dust grains to house-sized boulders, orbiting silently in a flat disk around the planet. Passive, inert, a beautiful structure held in place by gravity, casting shadows reflecting light. That picture is incomplete. During the grand finale dives, as Cassini flew through the gap between the planet and the innermost D-ring, its instruments detected an electric current flowing between the ring system and Saturn's upper atmosphere. A live electrical current moving through the space between the ring and the planet. The rings are not passive, they are electrically connected to Saturn below. Here is how it works. Saturn's magnetic field extends outward from the planet and threads through the ring system. The ring particles are not neutral objects sitting quietly in that field. They interact with it. Ultraviolet radiation from the star ionizes some of the material at the ring's surface, creating free electrons and ions. Saturn's magnetic field lines connect the rings to specific latitudes of the upper atmosphere. Charged particles from the rings travel along those field lines and rain down into the atmosphere. This process, called ring rain, had been predicted theoretically but was only confirmed by Cassini measurements. The rings are effectively trickling material into Saturn's atmosphere along magnetic channels. The electric current Cassini detected flows in the same channels. It is a circuit. The rings sit at one end. Saturn's ionosphere, the upper conducting layer of the atmosphere, sits at the other. Current flows between them along the magnetic field lines connecting them. The amount of current is small compared to the total electromagnetic energy of Saturn's magnetosphere. but its existence changes the conceptual picture fundamentally. The rings are participants in Saturn's electromagnetic system. They are not just decoration, they are a component. What are the implications? For the magnetic field itself, the current from the rings is too small to meaningfully alter the large-scale structure of the main dipole. Its contribution to the overall field is a tiny perturbation. But for Saturn's atmosphere, the effect is measurable. The ring rain deposits charged material at specific latitudes, which affects the chemistry and electrical behavior of those atmospheric regions. Observations with the Hubble Space Telescope had detected faint infrared bright bands in Saturn's upper atmosphere at the latitudes corresponding to ring rain. Cassini confirmed those bands were real and connected to the ring current. This electrical coupling between the rings and the planet also raises a question that planetary scientists are still working on. Does the ring system interact with the shallow dynamo? The shallow dynamo operates in the semiconducting layer just below the ionosphere. The ring current feeds into the ionosphere. Whether these two systems influence each other is an open research question. What is certain is that Saturn's electromagnetic environment is far more interconnected than anyone imagined before Cassini. The deep metallic hydrogen dynamo, the helium rain filter, the shallow wind-driven dynamo, the ring current, these are not separate phenomena. They are a system, and at the center of that system is a mystery that no layer of Saturn has yet explained. A mystery about which half of the planet is magnetically dominant, and why. If you took every measurement of Saturn's magnetic field and used them to calculate where the center of that field sits geometrically, you would find it, and then you would discover that it is in the wrong place. The center of Saturn's magnetic dipole is not at the center of the planet. It is shifted north by approximately 1,750 miles. To feel what that means, picture a sphere the size of Saturn, roughly 72,000 miles in diameter. Now imagine the center of its magnetic field sitting more than 1,000 miles north of the geometric center of that sphere. For a field that appears otherwise almost perfectly symmetric when viewed from east to west, the north-south offset is significant and unexplained. This offset was confirmed by the Cassini grand finale measurements. It appeared consistently across all 22 dives, at every altitude, in every direction. The northward shift is real, and it has a measurable consequence. Saturn's magnetic field is slightly stronger in the southern hemisphere than in the northern. If you stood at Saturn's south pole with a magnetic field detector, you would measure a stronger field than if you stood at the North Pole. The southern hemisphere sits slightly closer to the offset magnetic center and therefore experiences more of the field's intensity. On Earth, a similar offset exists, though smaller. Earth's magnetic dipole is also shifted slightly from the geometric center. Scientists attribute it to asymmetries in the liquid iron outer core, where the convection pattern is not perfectly uniform between hemispheres. For Saturn, the cause of the north-south offset is a confirmed unknown. Several hypotheses exist. One possibility involves asymmetric heat flow from the interior. If Saturn's core releases more heat from one hemisphere than the other, the convective patterns in the metallic hydrogen dynamo could be asymmetric between north and south, even while remaining nearly symmetric in the east to west direction. The dynamo would then generate a magnetic field whose center is offset in the north-south direction. Another possibility involves the helium rainout layer being distributed unevenly between hemispheres. If the filter layer is thicker or more effective in one hemisphere, it could dampen the field more on that side, shifting the apparent center of the field. A third possibility connects to the shallow dynamo. Saturn's atmospheric jet streams are not identical in the northern and southern hemispheres. If the shallow dynamo driven by those jets generates slightly different signals north and south of the equator, it could contribute a net offset to the overall field. None of these explanations has been confirmed. The offset is a measured fact. Its cause is still open. And sitting right next to this mystery is another one. To calculate the offset, scientists need to know exactly where Saturn's center of rotation is, and to know that, they need Saturn's true rotation rate. Which brings up the single most embarrassing unknown in outer planet science. After decades of spacecraft visits and thousands of scientific papers, nobody actually knows how fast Saturn spins. That mystery turns out to be even stranger than the magnetic tilt itself. Every child learns that Saturn takes about 10.5 hours to complete one rotation. It is in textbooks, it is on classroom posters. It is stated as fact on countless science websites. It is also not confirmed. Saturn's true interior rotation rate, the actual spin of the deep planet beneath the clouds, remains one of the most embarrassing open questions in planetary science. After Pioneer 11, 2 voyages and 13 years of Cassini, scientists still cannot give a definitive answer to something as basic as how fast Saturn turns. Here is why. On Earth, measuring the rotation rate is simple. The planet has a solid surface, you pick a landmark, watch it go around, and time it. Done. Saturn has no solid surface. The clouds rotate at different speeds depending on latitude. The equatorial winds blow much faster than the winds at the poles. There is no fixed feature to track, so scientists needed another method. For gas giants, the traditional solution is to use the magnetic field. A planet's magnetic field is anchored to its deep interior. As the planet spins, the field spins with it. If the field has any asymmetry, any slight wobble or directional feature, it broadcasts a repeating radio signal tied to that rotation period. Measure the radio period, and you have the interior rotation period. This method works perfectly for Jupiter. Jupiter's magnetic field has a clear tilt and a well-defined asymmetry. Its radio emissions repeat with a rock-steady period of 9 hours and 55 minutes. Scientists trust it completely. For Saturn, there is an immediate problem. Saturn's magnetic field is nearly perfectly symmetric. A symmetric field produces no directional asymmetry. It has no wobble to broadcast, so in principle, Saturn should emit no repeating radio signal tied to rotation at all. But it does. Saturn broadcasts a radio signal called Saturn kilometric radiation at a period close to 10 hours and 45 minutes. This signal repeats. Scientists used it as Saturn's rotation clock for decades. Then Cassini measured it again, and the period had changed. The voyagers measured the radio period at 10 hours and 39 minutes and 22 seconds. Cassini, arriving 25 years later, measured it at 10 hours and 47 minutes and 6 seconds. A difference of nearly 8 minutes, roughly 1% longer. A planet cannot actually slow its rotation by 1% in 25 years. That would require an extraordinary amount of external force and would violate conservation of angular momentum. The planet did not slow down. Something in its magnetosphere changed the radio signal instead. The leading suspect is Enceladus, a moon that continuously injects water vapor into Saturn's magnetic field. That plasma loads the magnetic field unevenly and can shift the radio emission period independently of the planet's true spin. The signal is real, but it is not a clean clock. Without a reliable clock, every dynamo model that depends on knowing Saturn's rotation rate carries a fundamental uncertainty. The true interior spin rate could differ from any currently cited value by an unknown amount. The number in the textbooks is an estimate, and what comes next is even more unsettling. Every planet with a magnetic field broadcasts radio waves. Earth does it. Jupiter does it. These emissions are generated by charged particles spiraling along magnetic field lines at the poles, releasing energy as radio waves in a process well understood by physicists. For Jupiter, the radio signal is so consistent and reliable that radio astronomers tracked Jupiter's rotation from Earth for decades before any spacecraft visited. The signal repeats like a metronome. Saturn's equivalent signal is called Saturn kilometric radiation. Kilometric because the wavelengths are roughly a kilometer long. in the low-frequency range of the radio spectrum. Cassini spent 13 years recording it. It pulses roughly once per rotation period, and for a long time, scientists trusted it as Saturn's clock. Then they noticed the clock was running differently than it had during the Voyager era. The Voyagers recorded the pulse period at 10 hours, 39 minutes, and 22 seconds. Cassini measured it at 10 hours, 47 minutes, and 6 seconds, a drift of nearly 8 minutes, 1% of the total period. Scientists immediately began ruling out explanations. A 1% change in planetary rotation would require the kind of braking force that does not exist in the outer solar system. The planet itself had not slowed, so the signal was changing independent of the planet. The investigation pointed toward Enceladus. Enceladus is a moon roughly 300 miles in diameter, smaller than the state of Arizona. Its surface is covered in bright white ice. Beneath that ice sits a liquid water ocean, kept warm by tidal heating from Saturn's gravity. At the south pole of Enceladus, hundreds of geysers shoot water vapor, ice particles, and organic molecules hundreds of miles into space. That material does not simply fall back down. A significant fraction of it escapes Enceladus entirely and enters Saturn's magnetosphere, where Saturn's magnetic field ionizes it and sweeps it into a rotating plasma torus, a donut-shaped ring of charged particles circling the planet. This plasma is not evenly distributed. It concentrates at certain latitudes and longitudes. As it rotates within Saturn's magnetic field, it creates a rotating pattern of density and electrical current that generates its own radio signal, independent of the planet's true rotation. That additional signal mixes with Saturn kilometric radiation. It shifts the measured period. It is not a clock. It is a clock that has been tampered with by a moon the size of Arizona. The consequence for dynamo models is significant. Every model that uses the rotation period as an input must acknowledge that the currently available rotation measurements are suspect. The deep interior of Saturn may be spinning faster or slower than any published estimate suggests, and without knowing the true spin rate precisely, the mathematical constraints on dynamo models are looser than scientists would like. Enceladus, a small geologically active moon, has effectively hidden Saturn's interior from one of the key diagnostic tools planetary scientists rely on. And Enceladus has done something else to Saturn's magnetic field. Something larger, something that reshaped the entire magnetic bubble surrounding the planet. Saturn's magnetic field is nearly perfectly symmetric. A symmetric field rotating symmetrically should produce no repeating pattern in the surrounding magnetosphere, no periodic signal, no pulse. And yet Saturn's magnetosphere pulses. Everywhere scientists look in Saturn's magnetic bubble, they find oscillations repeating near the 10.5-hour rotation period, variations in magnetic field strength, variations in the density of charged particles, variations in radio emissions, variations in the flow of plasma, all of them pulsing, roughly synchronized, at approximately the rotation period. These are called planetary period oscillations, and they exist in a magnetic environment that should theoretically produce none at all. The mystery deepens immediately. When scientists analyzed the oscillations in detail, they found that the northern and southern hemispheres of Saturn's magnetosphere pulse at slightly different periods. The north oscillates at one period, the south oscillates at a period roughly 1% different. Two separate pulse rates, one planet, and those two rates are not fixed. They drift relative to each other over time. Sometimes the northern and southern oscillations drift toward alignment, and when they partially synchronize, the signals constructively interfere, and the combined oscillation becomes stronger. At other times they drift apart, partially cancelling each other, and the oscillation weakens. The oscillations are also not confined to one part of the magnetosphere. They propagate throughout the entire magnetic bubble, detectable from the innermost regions near the rings, all the way out to the distant magnetopores, where the magnetic field meets the pressure of the solar wind. How does a symmetric field produce this? Several hypotheses have been proposed. One involves asymmetric heating of Saturn's upper atmosphere by its star. The star heats the day side of Saturn's atmosphere more than the night side. This creates temperature gradients that drive rotating current patterns in the ionosphere, the conducting upper layer of the atmosphere. Those rotating currents disturb the magnetic field and generate a periodic signal even when the underlying field is symmetric. Another hypothesis involves Enceladus. The plasma that Enceladus injects into Saturn's magnetosphere is not uniformly distributed. If the injection is concentrated at certain longitudes or latitudes, the uneven plasma load rotates with the field and generates a periodic signal. A third hypothesis involves internal asymmetries inside Saturn itself, perhaps in the shallow dynamo or in the distribution of the helium rainout zone between hemispheres. If something inside the planet breaks north-south symmetry at the rotation period, it would naturally produce two slightly different oscillation rates. None of these explanations fully satisfies the data. The dual-period oscillations, their time-varying drift, and their presence everywhere in the magnetosphere remain one of the deepest unsolved problems in Saturn science. Every model that has been proposed captures some features of the observations. None captures all of them. And the Moon, that is already interfering with Saturn's radio signal, is also responsible for reshaping the entire outer boundary of Saturn's magnetic field. A moon smaller than Great Britain is running the magnetic environment of the second largest planet in the solar system. Enceladus has a diameter of roughly 300 miles. Saturn has a diameter of roughly 72,000 miles. The size ratio between them is comparable to a marble sitting next to a school bus. And yet, Enceladus is injecting enough material into Saturn's magnetic field to fundamentally alter how that field behaves. Here is what Enceladus does. Its interior is heated by tidal forces from Saturn's gravity, which constantly squeezes and stretches the Moon as it orbits. That tidal heat keeps a liquid water ocean beneath the icy surface from freezing. At the South Pole, cracks in the ice called tiger stripes vent geysers of water vapor, ice particles, salt, and organic molecules into space at roughly 800 miles per hour. Much of this material escapes Enceladus's weak gravity entirely. It enters the space around Saturn and gets ionized by ultraviolet radiation from the star. Once ionized, the particles become electrically charged and are immediately grabbed by Saturn's rotating magnetic field. Saturn's magnetic field is enormous. It extends millions of miles into space. As it rotates with the planet, it sweeps up the charged material from Enceladus and spins it around Saturn in a vast, donut-shaped ring of plasma called the Enceladus plasma torus. The mass of material Enceladus dumps into this system every second is roughly 1,000 pounds, continuously, year after year. That accumulating plasma has mass, and mass resists being flung around by a magnetic field. The field has to do work to spin the plasma up to Saturn's rotation speed. This process is called mass loading. The plasma acts like a brake on the magnetic field lines. Where the plasma is densest, the field lines are most slowed. This uneven loading distorts the shape of Saturn's magnetosphere. At small scales, mass loading from Enceladus shifts the period of Saturn's radio emissions, as the previous chapter described. At large scales, mass loading reshapes the entire outer boundary of the magnetosphere and shifts key structural features of the field to positions that no model predicted before Cassini. And the most dramatic example of that shifting was confirmed just recently in a study published in 2026. Scientists examining Cassini data from the years 2004 through 2010 found that a specific feature of Saturn's magnetic field, one that should sit in a predictable location based on standard physics, was sitting somewhere completely different. The location it occupied had never been anticipated by any model before Cassini arrived, and understanding why it was displaced required rethinking the basic forces that shape Saturn's entire magnetic environment. Every planet with a magnetic field is surrounded by a protective bubble called a magnetosphere. The magnetosphere is the region of space where the planet's magnetic field dominates over the pressure of charged particles streaming in from the star. At the poles of that bubble, the magnetic field has a specific feature, a funnel-shaped opening where the field lines converge and charged particles from outside can enter and reach the upper atmosphere. This is called the magnetic cusp. On Earth, it is responsible for the auroras that appear near the poles. On Earth, the magnetic cusp sits near local noon, on the side of the planet directly facing the star. This makes physical sense. The solar wind pressure on that side compresses the magnetic field inward, which shifts the cusp toward the starward direction. The geometry is clean and predictable. Scientists expected Saturn's cusp to sit near local noon as well. It does not. A study published in Nature Communications in April 2026 used Cassini data collected between 2004 and 2010 to map the position of Saturn's magnetic cusp. The cusp was found consistently shifted to the afternoon side of the planet between 1 o'clock and 3 o'clock in local time. In some passes, it had drifted as far as 8 o'clock in the evening. That is not a small displacement. The cusp was sitting hours away from where physics predicted it should be. The cause involves two features unique to Saturn among the planets we have studied closely. First, Saturn rotates extraordinarily fast. Its day is only 10.5 hours long. That rapid spin creates powerful centrifugal effects inside the magnetosphere. The rotating magnetic field flings plasma outward toward the equator, which stretches and distorts the field lines away from their expected positions. Second, Enceladus continuously loads that rotating field with fresh plasma. The sheer volume of material being swept around by Saturn's rotating magnetic field adds to the centrifugal effect. The combined result is that Saturn's magnetosphere is not shaped primarily by the pressure of the stellar wind, the way Earth's is. It is shaped primarily by centrifugal force from the planet's own rotation. Those centrifugal forces push the magnetic field structure toward the evening side. They drag the cusp away from noon. The 2026 study confirmed something that theorists had predicted, but never directly verified. Saturn operates in a rotation-dominated magnetospheric regime. The planet's spin is so dominant that it overrides the stellar wind pressure that governs Earth-like planets. This has direct implications for understanding other worlds. Rapidly spinning gas giants around other stars likely operate in the same regime. Saturn gives scientists a nearby well-studied example of rotation-dominated magnetosphere physics. Every exoplanet model that includes a fast-spinning giant now has a confirmed reference point. But the lopsided cusp is only the surface of what this finding reveals. The real implication goes deeper into what controls magnetic environments across the entire galaxy. On Earth, the stellar wind controls the shape of our magnetic shield. The stellar wind is a constant stream of charged particles flowing outward from our star at roughly 1 million miles per hour. When those particles hit Earth's magnetic field, they compress the field on the starward side and stretch it out on the opposite side into a long tail. The result is a magnetosphere shaped like a comet, rounded on one side, elongated on the other. That shape is determined by the balance between the stellar wind pressure pushing inward and the magnetic field pressure pushing outward. On Earth, and on most planets, scientists had studied before Cassini reached Saturn. The stellar wind wins the basic tug-of-war. It defines the geometry. Saturn runs the same basic setup, but with one critical difference. It spins 13 times faster than Earth. That speed changes everything. When a planet spins fast, its magnetic field spins with it. The field lines that extend out into the magnetosphere get dragged around in a circle. Plasma sitting in those field lines gets flung outward by centrifugal force, the same effect you feel on a spinning carnival ride when your body is pushed towards the outside. For Saturn, the plasma dumped continuously into the field by Enceladus sits in those spinning field lines and gets flung toward the equatorial plane. As that plasma accumulates in the equatorial region, It stretches the field lines radially outward. The equatorial field bulges. The magnetosphere becomes more disc-shaped, flattened in the direction perpendicular to the rotation axis. This is fundamentally different from the comet shape that stellar wind pressure creates. The 2026 cusp study quantified this directly. By mapping where the magnetic cusp sat over many separate Cassini passes, scientists confirmed that the cusp displacement correlated primarily with Saturn's rotational dynamics and the plasma load from Enceladus. The stellar wind pressure was a secondary factor, not the primary one. The technical label for this is a rotation-dominated magnetosphere, as opposed to a solar wind-dominated one. Earth is firmly in the second category. Saturn is firmly in the first. Jupiter operates in a similar rotation-dominated regime, which scientists suspected, but Saturn confirmed more cleanly, because Cassini's long mission provided far more data than any Jupiter orbiter has yet accumulated. The significance goes beyond Saturn. Exoplanets are now being discovered with magnetic fields, detected indirectly through radio emissions and atmospheric interactions. Many of these planets are hot Jupiters, gas giants orbiting very close to their stars, spinning at various rates. Understanding whether a given planet is rotation-dominated or wind-dominated in its magnetospheric regime is critical for modeling its habitability, atmospheric retention, and how it interacts with its star. Saturn, sitting within our solar system, and thoroughly studied by Cassini, is the best laboratory scientists have for understanding rotation-dominated magnetospheres. Every model developed using Saturn's data can now be tested against exoplanet observations, and those models now face an even harder challenge, because explaining how Saturn's nearly perfect magnetic tilt, its lopsided cusp, its dual-period oscillations, and its shallow dynamo all coexist in a single coherent system requires understanding physical processes that science only recently began to explore. For most of human history, the only magnetic field scientists could study closely was Earth's. Then spacecraft gave us Jupiter, Saturn, Uranus, Neptune, and Mercury. 5 additional data points. 5 planets is still a tiny sample. The Milky Way contains an estimated 400 billion stars. Most of them have planets, and a significant fraction of those planets are gas giants, many of them spinning fast. For decades, planetary scientists have wanted to know, are the magnetic behaviors seen in our solar system universal, or are some of them special cases unique to this neighborhood? Saturn's grand finale data, combined with the 2026 cusp study, has started to answer that question. The rotation-dominated magnetosphere is likely common. Any gas giant massive enough to generate a large magnetic field and fast enough in its rotation will enter the same regime Saturn occupies. The stellar wind becomes secondary. The planet's own spin dominates. The magnetosphere flattens into a disk. The cusp drifts to the afternoon side. The practical consequence for exoplanets is direct. Astronomers have detected radio emissions from a small number of exoplanets and brown dwarfs, objects between planets and stars in mass. Some of those radio signals repeat periodically, which could indicate rotation-dominated magnetospheres similar to Saturn's. Using the physics confirmed by Cassini and the 2026 study, scientists can now build models that translate those radio signals into estimates of the planet's rotation rate, magnetic field strength, and plasma environment. This is how Saturn becomes a template for the galaxy. Every exoplanet with a known radio signal can now be compared against Saturn's confirmed behavior. Does it show the same afternoon-shifted cusp signature? Does its radio period drift the way Saturn's does? Is there evidence of mass loading from an active moon or internal volcanic activity? The answers to those questions, read through the Saturn template, allow scientists to infer interior structures, moon activity, and atmospheric conditions on worlds they can never visit. There is also a deeper implication for habitability. Magnetic fields protect atmospheres. A planet with a strong magnetic field deflects stellar wind particles that would otherwise strip away the atmosphere over geological timescales. Mars, which lost most of its magnetic field billions of years ago, subsequently lost most of its atmosphere. Earth's field has helped preserve conditions for life. For a moon orbiting inside a rotation-dominated magnetosphere like Saturn's, the protection works differently. The magnetosphere does not just deflect stellar wind. It creates a complex plasma environment that bombards the surfaces of moons within it with energetic particles. Enceladus and the other inner moons of Saturn sit inside that bombardment zone. Understanding how life could persist, or fail to persist, on a moon inside a rotation-dominated magnetosphere requires understanding the full system. Saturn provides the data, the galaxy provides the motivation, and the physics explaining how Saturn manages to sustain all of this while maintaining a nearly perfect magnetic tilt is still being worked out by researchers who have spent years on a single, strange mechanism that got a name only recently. Standard dynamo theory assumes that the magnetic field is generated by fully convective fluid. Hot material rises freely. Cool material sinks freely. The churning is vigorous, messy, and continuous. That vigorous convection generates the electrical currents that build and sustain the field. The helium rain filter theory accepts this picture for Saturn's deep dynamo. It proposes that below the helium rain out zone, the metallic hydrogen convects freely and generates a normally structured field. The filter layer above then strips out the tilted components before they reach the surface. A 2025 study proposed something different, something that challenges the boundary between the filter and the engine. The process is called semi-convection. Imagine a pot of water with a layer of dense, salty water at the bottom and fresh water above it. Heat the pot from below. The temperature gradient wants to drive convection. Hot water at the bottom wants to rise. But the density gradient from the salt fights back. The salty water at the bottom is denser than the fresh water above, which tends to keep it down, even when it is hot. The two competing forces, the temperature gradient driving convection upward and the density gradient fighting it, do not cancel each other out completely. Instead, they produce a compromise. Slow, layered, convective motions. Small cells of fluid overturn locally within thin layers, but the large-scale overturning that characterizes full convection does not occur. The fluid moves, but carefully. This is semi-convection. In Saturn's interior, the helium rain-out zone has exactly this character. The thermal gradient from the hot interior wants to drive convection upward through the helium rain zone. The compositional gradient, the increasing helium concentration with depth, creates a density stratification that resists large-scale overturning. The result should be semi-convective motions, slow, layered, confined to thin shells within the broader stratified zone. The 2025 study asked, can semi-convection generate a magnetic field? The answer from their numerical simulations was yes. The slow, layered motions in a semi-convective zone are still fluid motions in a conducting material. They still carry electrical current. And when the researchers ran their simulations in spherical shells designed to mimic Saturn's interior geometry, they found that semi-convection spontaneously produced a magnetic dynamo with realistic field strengths and a high degree of axis symmetry. The filter layer, rather than being only a passive barrier that blocks tilted field components from rising, might itself be generating a magnetic field. The stably stratified zone above the deep dynamo might be acting as a second engine, driven by semi-convection to the total field. If this is correct, Saturn's magnetic environment is even more layered than the grand finale data suggested. The deep metallic hydrogen dynamo runs below. The semi-convective dynamo runs within the filter zone above. The shallow wind-driven dynamo runs near the surface. 3 engines, 1 planet, 1 impossibly clean field at the surface. And a competing theory suggests the answer might be even simpler than all of this. Every proposed explanation for Saturn's near-zero magnetic tilt has focused on what happens deep inside the planet, the metallic hydrogen dynamo. the helium rain filter, the semi-convective layer. The approaches all share a common assumption that the tilt is shaped by processes below the clouds, hidden in the extreme interior. A 2022 simulation from a NASA team. Their model produced a magnetic dipole tilt of just 8/10,000ths of a degree, smaller than the current observational upper limit, without a thick helium rain filter, without exotic deep dynamo physics. Their mechanism was the jet streams. Saturn's atmospheric jet streams are among the most powerful in the solar system. Near the equator, winds reach over 1,000 miles per hour. The jets blow in alternating east-west directions at different latitudes, producing the visible band structure seen through a telescope. These winds are fast, consistent, and have persisted for as long as scientists have been observing Saturn. The question has always been how deep the jets penetrate. On a gas giant with no solid surface, the wind systems could in principle extend from the upper atmosphere all the way down into the deep interior. Or they could be a shallow atmospheric phenomenon confined to the outermost layers. Cassini's gravity measurements provided a partial answer. The detailed gravity field of Saturn, measured by tracking subtle shifts in Cassini's trajectory, showed anomalies consistent with winds extending down to roughly 3,000 miles below the cloud tops. Below that depth, the differential rotation appeared to fade, and the planet began rotating as a more solid body. 3,000 miles is deep in human terms, but it falls short of the metallic hydrogen layer, which begins around 12,000 miles down. If the jets only reach 3,000 miles, they do not directly touch the dynamo region. The 2022 model proposed a more indirect mechanism. The jets create differential rotation in the semiconducting hydrogen layer, the zone between the insulating molecular hydrogen and the metallic hydrogen below. Differential rotation in a conducting medium generates electrical currents. Those currents produce their own magnetic field, and critically, differential rotation in a region where the field is predominantly axisymmetric naturally tends to produce field contributions that are themselves axisymmetric. The jets, in this picture, act as a suppressor of non-axisymmetric field components. They do not generate the primary field, but their electrical currents preferentially cancel out the tilted components rising from the deep dynamo, leaving a nearly perfectly aligned field at the surface. The 2022 simulation achieved a tilt of 8/10,000ths of a degree using only this mechanism, assuming a low conductivity layer in the outer atmosphere. No exotic interior physics required. This result has not eliminated the helium rain hypothesis. Both mechanisms could be operating simultaneously, but it raised the possibility that the answer to Saturn's magnetic mystery is closer to the surface than anyone initially believed. And some researchers have proposed an explanation that is not gradual filtration or wind-driven suppression, but something far more dramatic, that Saturn's magnetic field is not being sustained at all. In the years before Cassini's grand finale, as the spacecraft made its close dives and the tilt measurement fell below 8,000ths of a degree, NASA mission scientist Linda Spilker said something that stopped the planetary science community cold. She raised the possibility that Saturn's magnetic field is slowly dying, that the near-zero tilt represents an advanced stage of decay, a field approaching extinction, not a field doing something exotic to sustain itself. The idea is based on a specific reading of Cowling's theorem. The theorem says a perfectly symmetric magnetic field cannot sustain itself. If Saturn's field is asymptotically approaching perfect symmetry, it may be slowly losing the ability to regenerate. Each measurement bringing the tilt closer to zero could be watching the dynamo engine wind down, not watching an exotic mechanism keep it alive. This would be an extraordinary finding. Planetary magnetic fields do die. Mars had 1 billion years ago and lost it, after which its atmosphere was stripped by the stellar wind. Earth's field has weakened by roughly 10% over the past century and a half, though scientists believe it is fluctuating toward a pole reversal rather than dying permanently. But a gas giant with a magnetic field actively fading toward extinction would be unlike anything observed in the solar system. To be clear, there is currently no supporting evidence for this beyond the tilt anomaly itself. Saturn's magnetic field strength is not decreasing in any measured way. The field's magnetic moment, that 600 times Earth figure, shows no signs of decline across the decades of spacecraft measurements. A dying field would typically weaken globally over time. Saturn's has not. The excess heat Saturn radiates is also inconsistent with a dying dynamo. A weakening dynamo generates less energy, which should translate into less internal heat output. Saturn's 2.5 times excess remains consistent with an active, healthy interior process. What the dying field hypothesis correctly identifies is the conceptual strangeness of the situation. A tilt approaching zero is, in Cowling's framework, a field approaching the condition that makes self-sustenance impossible. Whether Saturn is approaching that limit from a state of healthy operation, maintained by the exotic mechanisms discussed in earlier chapters, or from a state of slow decline, is a question the available data cannot yet answer definitively. The dying field hypothesis remains open. It has not been confirmed. It has not been ruled out. It sits as one of several possible interpretations of the same dataset, and that ambiguity points to a deeper question. Is Cowling's theorem itself incomplete? Is Saturn bending a rule, or is the rule itself missing something? Thomas Cowling published his theorem in 1934. He proved, using the mathematics of electromagnetic induction in a conducting fluid, that a perfectly axisymmetric magnetic field cannot be maintained by dynamo action. The currents in such a system would always cancel each other out. The field would always decay. The key word is perfectly. Saturn's magnetic tilt is less than 7/1000ths of a degree. That is an extraordinarily small number, but it is not zero. 7/1000ths of a degree of asymmetry still exists. Technically, Cowling's theorem does not apply to a field with any non-zero tilt. Saturn has a non-zero tilt. Technically, it does not violate the theorem. But the spirit of Cowling's result is different from its strict mathematical boundary. The theorem describes a limit. As a field approaches perfect symmetry, the currents sustaining it become progressively smaller, and the field becomes progressively harder to maintain. The theorem does not say a slightly tilted field is impossible. It says the engine efficiency drops as the tilt approaches zero. For most dynamo models, a tilt of a few degrees is easy to explain. A tilt of less than 1 degree is difficult. A tilt of less than 1/100th of a degree requires increasingly exotic explanations: thick filter layers, differential rotation suppression, semi-convective engines. And a tilt of less than 1/1000th of a degree, which is where Saturn sits, is at the edge of what any current model can reproduce, while keeping all the other observations consistent. Some physicists have proposed that Saturn is revealing a loophole in Cowling's theorem that the 1934 proof did not fully account for. The theorem was derived for an idealized system, a uniform conducting fluid in a symmetric geometry, with convection driving the dynamo directly. Saturn's interior is layered, compositionally stratified, and has multiple distinct regions with different conductivities. The interaction between those layers might create sustaining mechanisms that the idealized Cowling proof does not capture. This is not a rejection of Cowling's result. It is an extension of it into territory the original proof was not designed to address. The 2021 Johns Hopkins helium rain simulations reproduced a field close to Saturn's observed symmetry, but required very specific interior conditions. The 2022 differential rotation simulation got the tilt even smaller, using a completely different mechanism. The 2025 semi-convection study introduced a third pathway. None of these mechanisms violates Cowling's theorem. They all operate in the regime where the tilt is non-zero, just extremely small. What Saturn may be demonstrating is that the transition from clearly dynamo-sustaining to theoretically unsustainable is far wider and more complex than the simple limit Cowling described. The near-zero zone is scientifically rich, full of competing mechanisms, and poorly mapped. Saturn is sitting exactly in that zone, and it has been sitting there quietly for billions of years. The tools to understand it fully may not yet exist, but one thing confirmed by Cassini's ring data is already forcing scientists to reconsider the entire foundation of Saturn's interior structure. For most of Saturn's scientific history, the standard model of its interior looked like this: a compact, dense, rocky and iron core roughly the size of Earth, or a few times Earth's size, surrounded by layers of metallic hydrogen and molecular hydrogen, clean layers, clear boundaries, a sensible structure for a gas giant. Then scientists learned to use Saturn's rings as a seismograph. A seismograph detects vibrations in the ground. On Earth, seismographs pick up earthquakes and allow geologists to map the interior by watching how vibrations travel through different layers. The same principle works for planets. Internal oscillations produce waves that propagate through the interior and leave fingerprints at the surface. Saturn oscillates internally. Its interior vibrates in specific patterns called normal modes, driven by the same dynamics that power the dynamo. Those vibrations travel outward and reach the rings. The rings respond. Specific ring structures, the density waves seen in Cassini's ring images, are driven by resonances with Saturn's internal oscillation frequencies. By mapping which ring structures correspond to which oscillation frequencies, scientists can infer properties of the internal layers that generated them. This is ring seismology. The results were surprising. The oscillation patterns detected in Saturn's rings are inconsistent with a compact, dense core surrounded by clean fluid layers. They are consistent with a diffuse, extended core that grades gradually outward rather than ending sharply. The best fit models suggest Saturn's core may be spread across as much as 60% of the planet's total radius, a fuzzy ball of mixed rock, metal and fluid, not a compact stone at the center, but an enormous blended interior region that transitions gradually into the surrounding layers. The diffuse core of that size would contain a substantial fraction of Saturn's total mass in a region far larger than the compact core models assumed. It would change the pressure and temperature distribution throughout the interior. It would alter the depth at which metallic hydrogen forms. It would change the geometry of the dynamo region. Every dynamo model built on the assumption of a compact core would need revision. The ring seismology result is not yet in complete agreement with other measurements. Gravity data from Cassini suggests a core mass somewhere between 9 and 22 times Earth's mass, a wide range that reflects real uncertainty. Ring seismology points to roughly 17 times Earth's mass. The two methods give different pictures, and neither measurement technique is precise enough yet to fully resolve the conflict. What is clear is that the standard model of Saturn's interior, the one underlying most dynamo models and most explanations of the magnetic tilt, was built on assumptions that may be significantly wrong. A fundamentally different interior structure changes what mechanisms are physically possible inside Saturn and which ones are ruled out. The answer to the magnetic mystery may depend on getting the interior structure right first. Science progresses by measuring the same thing multiple ways. When independent methods agree, confidence grows. When they conflict, something interesting is usually hiding in the gap. Saturn's interior mass distribution has been measured by two methods. They do not fully agree. The first method uses gravity. As a spacecraft orbits a planet, it follows a trajectory determined by the planet's gravitational field. If the planet's interior is not perfectly uniform, its gravity field will have subtle irregularities that shift the spacecraft's path by tiny amounts. Cassini's radio signal was tracked with extreme precision over its entire mission, and those tiny trajectory shifts were used to map Saturn's gravity field in detail. The gravity measurements are sensitive to how mass is distributed within the planet. They produce constraints on the core mass and the density distribution of the interior layers. The Cassini gravity data places Saturn's core mass somewhere between 9 and 22 times Earth's mass. That wide range reflects the fact that different interior models can produce similar gravity signals, so the data alone does not pin down a unique solution. The second method uses ring seismology. Saturn's rings respond to internal oscillations, and mapping those responses gives a different window into the interior. The ring seismology analysis points toward a core mass of roughly 17 times Earth's mass, and crucially, toward a diffuse extended core rather than a compact one. 17 times Earth's mass falls within the gravity range of 9 to 22. In that sense, the two methods are not completely inconsistent, but the structural picture they imply is quite different. Gravity models that fit the data tend to favor more compact core configurations. Ring seismology favors a diffuse one. A compact core surrounded by clean fluid layers produces a different dynamo geometry than a fuzzy extended core blending gradually into the surrounding material. The conflict matters because dynamo models are sensitive to interior structure, the depth at which metallic hydrogen forms, the thickness of the transition zone between molecular and metallic hydrogen, the geometry of the helium rainout region. All of these depend on knowing the core's size and density profile accurately. If the core is compact, the dynamo geometry looks one way. If the core is diffuse and extended across 60% of the planet's radius, the dynamo geometry looks fundamentally different. The locations and thicknesses of the critical internal layers shift. The helium rainout zone sits at different depths. The shallow dynamo operates in a different electromagnetic environment. Current data cannot resolve this conflict definitively. Both methods have uncertainties. Ring seismology is still a developing technique, and the relationship between ring structures and interior oscillations involves assumptions that are being refined. Gravity modeling depends on the assumed form of the interior model, and different assumptions give different answers within the observational uncertainty. Resolving the conflict requires better data, and getting better data requires a new mission to Saturn, one that no space agency has yet sent on its way. 4 decades, 4 spacecraft, thousands of scientific papers. It is time to account clearly for what is actually known. Some things are confirmed beyond reasonable scientific doubt. Saturn's magnetic dipole tilt is less than 0.007 of a degree. This has been measured by Pioneer 11, Voyager 1, Voyager 2, and Cassini across 45 years with independent instruments. The tilt is real and genuinely extraordinary. A stably stratified layer at least 2,500 miles thick exists above Saturn's deep dynamo. Cassini's grand finale data confirmed its presence through the structure of the magnetic field at close range. Saturn's magnetic dipole center is offset approximately 1,750 miles north of the planet's geometric center, confirmed across all grand finale passes. Saturn radiates roughly 2.5 times more energy than it receives from its star, confirmed by multiple spacecraft and ground observations. A secondary shallow magnetic signal banded by latitude sits within the main field, corresponding to atmospheric jet stream widths, confirmed by grand finale magnetometer data. An electric current flows between Saturn's innermost D-ring and the upper atmosphere, confirmed by Cassini. Saturn's magnetic cusp is displaced to the afternoon sector, between 1 and 3 o'clock local time, and sometimes further, confirmed by the 2026 Nature Communications study. Now for the theories. The helium rain filtration layer is the leading explanation for the near zero tilt. It is supported by multiple independent simulations and consistent with the confirmed excess heat output and the confirmed stably stratified layer. It has not been directly observed. It remains a theory with strong supporting evidence. The shallow wind-driven dynamo is tentatively supported by grand finale data. The banded magnetic signal matches the jet stream pattern. The mechanism is physically plausible. It is not yet confirmed as a dynamo in the strict sense. Semi-convection within the stratified layer is a newer hypothesis with supporting numerical simulations. It is promising, but not yet tested against the full Cassini dataset. differential rotation suppression of the non-axisymmetric field components is supported by the 2022 simulation. It remains a competing hypothesis rather than a confirmed mechanism. Now for the confirmed unknowns. Saturn's true interior rotation period is unknown. The radio signal proxy has been shown to be unreliable. The cause of the north-south dipole offset of 1,750 miles is unknown. The origin of the planetary period oscillations, and specifically why they have two separate and drifting periods in the northern and southern hemispheres, is unknown. The detailed internal structure, specifically whether the core is compact or diffuse, remains unresolved between competing measurement methods. Whether Saturn's field is stable and sustainable for billions more years, or whether it is in a slow decline, is unknown. The science of Saturn's magnetic field is rich with confirmed facts, strong theories, and deep mysteries. None of the mysteries cancels the confirmed facts. None of the theories has displaced the others entirely. The picture is genuinely incomplete. Cassini ended on September 15, 2017. Since that day, no spacecraft has been within 1 billion miles of Saturn. As of 2026, no mission to Saturn is en route. The last data from Cassini is still being analyzed. Papers are still being published. But the observations themselves stopped years ago. Scientists know what a next-generation Saturn mission would need to accomplish. They have laid it out in detail across numerous published mission concept studies and planetary science decadal surveys. The first priority would be a more advanced magnetometer, one capable of measuring magnetic field structures, smaller and fainter than anything Cassini detected. The grand finale revealed the banded shallow dynamo signal only because of its close passes. A future orbiter spending months or years at similarly close distances with better instrument sensitivity could map that shallow signal globally rather than in the limited snapshot Cassini provided. The second priority would be interior probes. Cassini measured the magnetic field at the surface of the planet and inferred interior structure from gravity and ring seismology. A future mission might deploy atmospheric probes capable of descending into Saturn's atmosphere to directly measure temperature, composition, and wind profiles at depth. The Galileo spacecraft dropped a probe into Jupiter's atmosphere in 1995, and the data from those 90 minutes of descent transformed Jupiter science. A Saturn atmospheric probe could do the same. The third priority would be resolving the rotation rate. A more sensitive magnetometer, combined with very long baseline radio tracking of the spacecraft, could potentially detect tiny asymmetries in Saturn's field that Cassini could not resolve. Even a confirmed asymmetry smaller than 0.007 of a degree would allow scientists to calculate the true interior rotation period. Alternatively, seismology measurements taken continuously over years rather than months could sharpen the ring seismology analysis enough to resolve the core structure debate. The fourth priority would be extended coverage of the moons, particularly Enceladus. A dedicated Enceladus orbiter could map the plasma injection rate, its variation over time, and its effect on the magnetospheric oscillations directly. Understanding the planetary period oscillations requires understanding Enceladus's contribution precisely, and that requires being there continuously rather than in passing. Mission concepts have been proposed. A Saturn probe mission was among the recommendations of the 2023 to 2030 to 2032 Planetary Science Decadal Survey, the document that sets NASA's science priorities for a decade. Actual mission development, funding, and launch typically take 15 to 25 years from concept to arrival. Any spacecraft approved in the mid-2020s would reach Saturn no earlier than the 2040s. Until then, scientists will continue working with Cassini's data. There are still analyses underway. There are still papers in preparation. The archive is enormous and has not been fully mined. Saturn will wait. It has been keeping the secret for billions of years. A few more decades will not change that. Saturn is not hospitable to life as we understand it. Its atmosphere is a crushing, toxic, wind-torn environment, Its surface, such as it is, does not exist in any meaningful solid sense. No organism we can conceive of could survive there. But the magnetic mystery Saturn presents has direct implications for where life might exist elsewhere, and whether those places are shields. On Earth, the magnetic field deflects the constant stream of energetic charged particles flowing from our star. Without it, those particles would reach the upper atmosphere and strip it away over millions of years. Mars lost its magnetic field roughly 4 billion years ago. Its atmosphere thinned, its surface liquid water dried up. Life, if it ever existed there, lost its protective layer. The relationship between magnetic fields and habitability is not hypothetical. It is the story of Mars and Earth side by side. For planets around other stars, scientists cannot yet measure magnetic fields directly in most cases, but they can make inferences from radio emissions, from atmospheric loss rates, and from the orbital and physical properties of those planets. And one of the key variables is how a planet's magnetic field forms and sustains itself. Saturn demonstrates that a planet can sustain a powerful magnetic field through exotic interior mechanisms, helium rain, semi-convection, layered dynamos, in a configuration that no standard model would have predicted. If one planet in our solar system can do this, others around other stars almost certainly can too. For gas giant moons, the implication is even more direct. Enceladus orbits inside Saturn's magnetosphere and is partially shielded by it. The magnetic field that deflects stellar wind particles is the same field that was the central mystery of this entire story. A moon like Enceladus, with its liquid water ocean, exists in a habitable zone defined partly by Saturn's magnetic protection. If scientists can understand how Saturn sustains its field through exotic interior physics, they can model whether other gas giants around other stars are sustaining similar shields and whether moons inside those shields could maintain liquid water oceans. The 2026 CUSP study added another layer. It established that rapidly rotating gas giants operate in rotation-dominated magnetospheric regimes that differ fundamentally from Earth-like planets. The protection those magnetospheres offer their moons is shaped differently. The particle bombardment patterns are different. The zones of relative safety are different. Understanding this regime is essential for assessing whether moons like those of Jupiter and Saturn, or their counterparts around other stars, could harbor life. Saturn's near-zero magnetic tilt is a mystery that has resisted explanation for 45 years. It has forced a rethinking of planetary dynamo theory, revealed exotic interior processes operating at scales and pressures that have no counterpart on Earth, and produced an entirely new picture of how a magnetic field can be structured, filtered, and sustained. The mystery is not solved, but every piece of it uncovered has expanded what scientists consider possible inside planets. And a larger space of the possible means more worlds where the conditions for life might exist, waiting to be found. Saturn kept its secret well. We are only beginning to understand what it has been hiding.